Okay, good morning everyone. We have discussed up till now the design of stable channels by method of Kennedy's theory, then by Lacey's theory. We have also discussed what are the limitations of these theories. Now today we will be discussing about tractive force approach for the design of stable channels. The movement of sediment at bed is caused by a force exerted on its grains by the flowing water. This force is known as tractive force, and it is equal to the component of weight of water in the direction of flow. For uniform flow, the mean tractive force per unit area or the shear stress is given by tau is equal to gamma W into R into S, where tau is the tractive force per unit area given in kN per meter square. Gamma W is unit weight of water in kN per meter cube. R is the hydraulic radius in meter and S is the bed slope. The critical tractive stress tau C is the maximum tractive stress that will cause the movement of the bed material forming the channel bed on a level surface. The critical tractive stress is a function of sediment concentration and the average particle size of the bed material. Several investigators gave the expression for the critical tractive stress. For example, the first equation is given by Shield. It is tau C is equal to 0.06 into gamma W into bracket G minus 1 into D, where tau C is in kN, the critical tractive stress in kN per meter square, gamma W unit weight of water in kN per meter cube, G is the specific gravity of sediment, approximately taken as 2.65. D is the grain diameter in meter. So by using G is equal to 2.65, gamma W is equal to 9.81 kN per meter cube, tau C is equal to 0.98 times D. The second equation is given by White. He gives critical tractive stress tau C is equal to 0.801 times D, where D is again a grain diameter in meter. Third equation given by Lane, which is tau C is equal to 0.78 into D. So using the above equations, knowing the grain diameter, one can obtain the critical tractive stress. The critical tractive stress on sloping surface is less than that at a level surface. Thus, they show tau S upon tau L is given as tau S upon tau L is equal to cos phi into bracket 1 minus tan square phi upon tan square theta, where tau S is the critical tractive stress on sloping surface, tau L is the critical tractive stress on level surface, phi is the angle of sloping surface with horizontal, theta is the angle of repose of the soil. So in this manner, using the tractive force approach, one can design the stable channel. Let us take a numerical example on the design of unlined channels in alluvial soils by tractive force approach. So the data given is discharge of 50 cubic with following details. The bed slope is 1 is to 5000. Side slopes are 0.5 horizontal to 1 vertical. Manning's coefficient n, that is 0.0225, and the permissible tractive stress based on grain size is given as 0.0025 kilonewton per meter square. So using the equation for the critical tractive stress tau C equal to gamma W RS, putting the value of tau C and gamma W and slope, the hydraulic radius R is computed as 1.27 meter. By using the Manning's formula, V is equal to 1 by N R raised to 2/3 S raised to half. Calculate the velocity of the flow, that comes out to be 0.737 meter per second. Now using the continuity equation Q is equal to A into V, obtain the area of cross section of the channel A is equal to Q by V. So Q is given as 50 cubic divided by the velocity calculated by Manning's formula 0.737, which is equal to 67.82 meters square. Now P is equal to perimeter P is equal to A by R. So the area is 67.82, R calculated is 1.27, therefore P is 53.540 meters. Now using the equation for the area, A is equal to BD plus 0.5 D square, which is equated to area calculated earlier, and the perimeter P is equal to B plus D root 5, which is equated to perimeter 53.40. By solving equations 1 and 2, we can obtain the values of D and B. D is equal to 1.33 meters and B is equal to 50.40 meters. So this example will explain you the tractive stress method of design of stable channel. Now let us discuss the Blench method of design of channels. Blanch argued that the Lacy's equations ignored the fact that the relative importance of the sides and the bed could be different for different channels. A single silt factor may not be adequate over a wide range of bed and side conditions. In order to take this variation into account, Blanch introduced two coefficients known as side factor Fs and the bed factor Fp, which were defined as given below. So Fp is equal to U square by D, where U is the mean velocity of the flow and D is the depth of the flow. And Fs is defined as U cube upon W, in which W is the mean width, such so that A will be equal to W into D. Blanch also proposed the following slope equation, which is U square upon GDS is equal to 3.63 into bracket U into W upon nu raised to 0.25, where U is the mean velocity of the flow, W is the mean width, then nu is the viscosity, D is the depth of flow, S is the slope, and G is the acceleration due to gravity. Further, Blanch wrote his equations in the following form for the design purpose. Thus, we have W, that is the mean width, which is given as Fb under root of Fb upon Fs into Q raised to half. The depth D of flow will be equal to Fs upon Fb raised to 1/3 into Q raised to 1/3, and slope S is equal to Fb raised to 5 by 6, Fs raised to half, nu raised to 1/4 divided by 11.91 Q raised to 1/6 into G. So this is the Blanch method of design of stable channels. Thank you.